Hello everyone and welcome to my talk for the Proseminar Experimental Physics about the Nobel Prize in Physics in the year 2003. I would like to start off this talk with a short introductory story about this man right here to the left. This is Heike Kamerlingh-Onnes. He was a Dutch physicist who was interested in the behavior of materials at very low temperatures, and he was actually a pioneer in these techniques. And he also developed a technique to liquefy helium, which happens at around 4.2 Kelvin, which was the lowest temperature measured at that time. And for this, he would then eventually receive a Nobel Prize too. And at this time, there was some discrepancy about the behavior of conductivity at low temperatures, because some people thought, well, if there is no temperature, there must be no kinetic energy, which means that the electrons should not be able to flow at all. And other people, including Onnes, said the opposite should be the case. And so Onnes took it upon himself to investigate this case and used liquid helium to cool down solid mercury and then measure the resistivity. And what he observed was astonishing, and he thought actually that his experiment must be faulty, that something went wrong, because he observed that resistivity completely vanished for mercury at 4.2 Kelvin. But what he saw was, as we now know, a very real phenomenon. And on this day, the 8th of April 1911, Heike Onnes discovered superconductivity. And by the way, this man to the right here is Johannes van der Waals, which is a name that you should also know. Almost 50 years after Onnes, the theory of superconductors and superfluids has been revolutionized, and not at last thanks to these three gentlemen who jointly received the Nobel Prize in Physics in 2003 for their pioneering contributions to the theory of superconductors and superfluids. The Nobel Prize went to the American-Russian Alexej Abrikosov, the Russian Vitaly Ginzburg, and the British-American Anthony Legget. In this talk, I will cover the following topics. At first, I want to give a short recap about the concept of superconductivity and also introduce superfluidity, because probably some of you have never heard of this before. Then I will give a short introduction about the lives and the contributions to the superconductivity theory by the different laureates. Then I will show some experiments on the vortex phase, which is a theory developed by Alexej Abrikosov. And the experiments are there to show or to prove that his theoretical predictions were right. And in the end, I want to take a step back and show the importance of the discovery of superconductivity and what it might have in store for us in the future. So, as most of you might remember, a superconductor is a perfect diamagnet, which means that if the superconductor is in the superconductive state, which is here denoted by state A, it will expel all external fields by creating supercurrents inside the material that produce an equal and opposite field inside the superconductor, which results in a net zero field inside it. A very interesting or a very important property in superconductors is the critical temperature, Tc, right here. This sets the temperature at which a transition from the normal conducting state to the superconducting state happens. Apart from the effect that the superconductor shows the Meissner effect, which is the effect that I just explained, is also the effect of zero resistivity, which I've discussed in the introduction. Right. We distinguish between two types of superconductors, type 1 and type 2 superconductors. A type 1 superconductor only has one phase transition, so one critical external field at which superconductivity vanishes, and one critical temperature. But for type 2 superconductors, there are actually two critical fields and an intermediate state, which is called the vertex state, or also the mixed state. In this state, there are some regions in the superconductor which are normal conducting, and these normal conducting regions form a lattice where magnetic flux quanta can pass through, which we will learn also in the section about Abrikosov. Yes, which shows very, very interesting properties. Then superfluids Superfluids are more or less the same principle, but the most important property of a superfluid is that viscosity vanishes completely when it transitions into the superfluid state. The most important superfluids are 3 and 4 helium. And 3 helium is a fermion, as 4 helium is a boson, which means that they condense a little bit differently into the superconducting state. 3 helium actually forms Cooper pairs, similar to superconductor where electrons form Cooper pairs, but here there are full atoms that form Cooper pairs. And for 4 helium, which is a boson, they can just condensate into Bose-Einstein condensate without any restrictions. And for 3 helium, this happens at around 2.7 millikelvin, which is a very low temperature. And for 4 helium, they condensate at 2.1 Kelvin. I will now present the laureates in chronological order, and the first one I will discuss is Vitaly Lazarovich Ginzburg. He was born in Tsarist Russia in 1916 and worked as a lab assistant after high school. He then went on to get a PhD at the Lebedev Institute in 1942, which was evacuated from Moscow to Kazan during the war. He stayed in Russia most of his life, but he had a very rough time in the beginning. Since he had Jewish heritage and he only received his title of professor years after he started lecturing in 1953 after Stalin's death. He received his share of the Nobel Prize for the development of the Ginzburg-Landau theory of superconductors, on which I shall elaborate in just a minute. The Ginzburg-Landau theory is based on the Landau theory of second-order transitions, which are continuous transitions from a higher to lower symmetry state, which is obviously the case for superconductors and thus a very appropriate description. And the idea is to expand the free energy functional with respect to an order parameter eta, which is a scalar, and then minimizing this free energy functional with respect to this order parameter, which gives us then a condition on the order parameter. And the functions a and b are phenomenological functions, which can be approximated by constants times a factor when the temperature is near the critical temperature. And we can see here directly that if the temperature is greater than Tc, the square becomes negative and we have non-physical solutions, which means that the order parameter must be 0 for temperatures higher than Tc and non-zero for temperatures lower than Tc. Then what Ginzburg did with this theory, and which was a genius move, which also his colleague Abrikosov said about it, is to replace the order parameter eta with an order parameter field. And this order parameter field looks like a wave function, which it turns out is actually a wave function if we look at BCS theory, which was developed only much later. Then the idea is the same. We expand the free energy functional in terms of this order parameter field, and we introduce the electromagnetic fields. And from this free energy functional, if we then minimize it, etc., we get the Ginzburg-Landau equations. I will not go into detail on how they did this, because I could do a whole talk just about the Ginzburg-Landau theory itself. So if you have questions that do not go too much into theory, please ask them in the comments. But what is important, or what is interesting about these Ginzburg-Landau theories, is that we have these factors of 2 in front of the masses, in front of the charges, which is no mistake, because how we learned in BCS theory, or how we were told in BCS theory, superconductivity happens if electrons form Cooper pairs, and Cooper pairs are pairs of 2 electrons, which is why this factor 2 here shows up. Right. And the most important thing that comes from Ginzburg-Landau theory is the Ginzburg-Landau parameter K. This constitutes of 2 very intrinsic lengths in the superconductor, which is for one the penetration depth here, which sets the exponential law for the decay of the external B field inside a superconductor, and the coherence length C, which sets the exponential law for which the small perturbations of the superconducting electrons regain their equilibrium value, or in other words, It is the length scale at which the superconducting density of states drops to zero near the surface of a superconductor. And there is a very interesting aspect about this Ginzburg-Lambda parameter, because it says if this parameter is smaller than 1 over square root 2, then we have negative interface energy, which would mean that that the system should be unstable against maximizing the number of interfaces, which was not observed in experiment. So it was believed that the order parameter, or the Ginzburg-Lambda parameter, can only be smaller than 1 over square root 2. And one of the people who investigated this case further was Alexej Abrikosov. Alexej Abrikosov was born in 1928 in Moscow in the Soviet Union, and he studied physics at the Institute for Physical Problems in Moscow, which is today known as the Kapitsa Institute, and he got his PhD there under Lev Landau, actually, who by then already had published his Ginzburg-Landau theory in 1950. And a fun fact, in 1975, Abrikosov should have come to Zurich as a professor after gaining his honorary doctor's title in Lausanne, which unfortunately for us never happened. In 1991, he then went to the United States, to Illinois, to teach and to research. He actually received also the American-Russian double citizenship. He received his share of the Nobel Prize for developing the theory of type 2 superconductors based on Ginzburg-Landau theory, explaining the phenomenon of vortex lattices in mixed phases. In university, Abrikosov had a roommate named Nikolai Savaritsky, and he was interested in examining the Ginzburg-Landau theory, or the predictions of the Ginzburg-Landau theory. And he did this by examining the dependence of the critical magnetic field on the film thickness and temperature of superconducting thin films to see if the results fitted. And it was believed, as I said before, that the Ginzburg-Landau parameter should be smaller than 1 over square root 2, which meant that the coherence length must be greater than the penetration depth. But what Savaritsky observed was that the opposite was the case for his sample. And so the order parameter, the Ginzburg-Landau parameter, had to be greater than 1 over square root 2. He then showed these results to Abrikosov, and he considered the case for the Ginzburg-Landau parameter to be greater than 1 over square root 2 and calculated the critical fields. And his data his results fit the data perfectly. And he investigated this case further, and he found that the periodic distribution of the magnetic field inside the superconductor in this newly formed phase would minimize the energy if they arranged in a lattice of magnetic flux quanta, which is shown here. And as he considered gauge invariance for the order parameter, which means rotations, which basically means rotations in a complex plane for the wave functions, he found that these solutions must be vortex solutions, which means in the end that we have supercurrents in the form of vortices, which means that they go in circles inside the superconductor, forming a normal conducting region inside the superconductor where flux quanta can penetrate the superconductor. And the superconducting region is distinguished from the normal conducting regions by these exact vortices. And actually, he did not expect such solutions, which is why he didn't publish his results until the 1960s, when he got wind that Feynman actually predicted also vortex solutions in superfluids. But as you can imagine, the communication between the East and West in the Cold War was not the best, to say the least. Last but not least, I will discuss the life and work of Anthony James Legget. He was born in 1938 in South London, and he studied physics at Oxford after already gaining a degree in classical studies there. He eventually received his PhD in Oxford in 1964 for his thesis on problems in the general area of liquid helium. And he traveled a lot. He liked to travel for his work, and he also taught in the United States, Japan, but also Ghana. And in 1983, he then accepted an offer from the University of Urbana in Illinois, where he has been a professor ever since. And he received his share of the Nobel Prize for his theory on anisotropic superfluids by considering multiple simultaneously spontaneously broken symmetries. And before I go further, I want to introduce these two concepts. So anisotropy means that a medium, or better said, isotropy means that a medium shares all properties in all directions of space. So anisotropy means that this symmetry is no longer there. And secondly, a symmetry is spontaneously broken when a state that is usually symmetric under a certain transformation goes in asymmetric state. And a very famous example is a ferromagnet, which below the Curie temperature has preferred directions of spin as opposed to above the Curie temperature, which means that we have a broken symmetry when we pass this certain temperature. And the fact that there must not be, or there doesn't have to be, an external magnetic field for this process to happen makes this symmetry breaking spontaneous. Now, note that at the time that Legget presented his new theory, BCS theory was well underway. And BCS theory is actually the first microscopic theory of superconductors, as opposed to Ginzburg-Landau theory, which was purely phenomenological. But Ginzburg-Landau theory can be derived from BCS theory. So Legget founded his task then to generalize the BCS theory to superfluids. And in original BCS theory, Cooper pairs are spherically symmetric, which is no longer the case for 3 helium, for example, as they form quasi-particles of atoms with clouds of other atoms, which renders the whole system anisotropic. Since the two partners in the Cooper pairs form a spin triplet in this case, the spin relative angular momentum is not zero, meaning that they point intrinsically in different directions, which is again anisotropic. And in order to understand the significance of anisotropic superfluids, we first have to appreciate the notion of spontaneous broken symmetries, which can be broken simultaneously for superfluids. In 3 helium, the rotational symmetry is broken due to the pairs being a spin triplet state. Then we have the orbital rotational symmetry, which is broken to the anisotropy of the Cooper pair wave function. And gauge symmetry is broken because below TC a particular phase or gauge is preferred. And thus 3 different symmetries are broken simultaneously. And the consequences of these contributions to the BCS theory led to the understanding of the effects that I showed in the beginning, that the superfluid can creep up walls of a container and flow on the outside of it, and also it can drip through containers where the fluid is in, which is a very peculiar effect and very interesting. And here I just wanted to show how broken symmetries can look like figuratively. Here in A we have a completely symmetric state, which means that, or an isotropic state, which means that it doesn't matter where we look, we always find spin and angular momentum in random directions. And here in the D example, we see that we have alignments of the spins, and also with angular momentums relative to these spins, and also inside a certain direction in space. It means that we have several broken symmetries. Right, so the Abrikosov theory predicted a 2-dimensional grid of penetrating external field flux tubes for which each field quantum passes. And Legget has proposed in 1964 to use neutron diffraction methods to try and measure this periodicity. And neutron scattering should resonate in your ears, because that's already a presentation that we heard from Uchin. And this was then put into practice by Cribier by using a technique on a pure niobium superconductor. At 4.2 Kelvin. The first critical field is at about 1400 Oersted, which is the unit for magnetic field flux in the CGS unit, and H2 is at about 2700 Oersted. They used neutrons with a wavelength of about 4.7 angstrom with a resolution of 1.3 angstrom. And they used liquid hydrogen to multiply these neutrons by, I think, tenfold. And then they measured the distribution of the neutrons that's scattering on this lattice, because the magnetic moments of these neutrons were affected by the varying distribution of the magnetic field inside the superconductor, such that they were deflected. And the deflection angles are usually very small, like in the order of a tenth of a degree, which is why this method is called small angle neutron scattering. And in Cribier's experiment, he measured the intensity of the refracted neutrons at an angle of about 8 degree minutes as a function of the applied field, which is shown here. And he also measured the Bragg peak intensity at different diffusion angles at an applied field of 1620 Oersted, which is shown here, and the 1620 Oersted is already in the vortex phase. And we can see very nicely here that the vortex phase is actually not stable. It decays little by little with more magnetic field, which I will also show a little bit later. And he found that there exists a periodic structure of induction whose period is a function of the applied field. And he did this by also helping to develop a technique which is still one of the state-of-the-art techniques when it comes to vortex measurements. And yes, I read this paper in French, and no, it was actually very interesting, and it is a very short paper, and I would suggest that you read it too. It's very interesting to also to read about this sort of physics in other languages. So small angle neutron scattering is still a technique used today, and as the principles stay the same, some adjustments or some progress has been made. So the neutron beams are monochromatized before they are shot at the target, where the beam is diffracted. The cross-section of the scattering process depends on the momentum transfer Q, which is again dependent of the spatial distribution of the flux tubes. Thus, if the diffraction pattern is studied, we find out a lot about the vortex lattice, and as for example the lattice structure. And we can do that by rotating the sample about a rocking angle omega, which then gives rise to these spectra. Another method that is often used is scanning tunneling spectroscopy, which is also something that you know from the talk from Sara. And STS uses the notion of quantum mechanical tunneling by applying a voltage between the metal tip and the superconducting sample, and this allows current to flow. And the result are local tunneling conductance spectra, as you see here. And STS is very powerful since it scans the surface directly and can thus measure the real space variation in the local quasi-particle density of states. And there are two ways you can do this. One is to move the tip across the sample and then measure the density of states, or you can alter the external magnetic field little by little in a controlled way, such that the vortex lattice actually moves inside the superconductor, and you can measure where they are. And by acquiring these continuous local tunneling conducting spectra, the changes in the local density of states can be detected under the tip in real time and in real space. And what we can observe in this way is how the vortex phase actually decays, which I mentioned a little bit earlier. So if the vortex state is in the perfect state, then it's a perfect hexagonal lattice, which means that each point or each flux, each vortex has 5 nearest neighbors. But as we increase the external field, we have more and more disclinations and dislocations, which means breaking of short-range symmetries, like that some vortices now have more or less nearest neighbors. And this happens continuously until we have sort of a glass-like state. And as I think Leila told about in her presentation about short range and long range symmetry, or short range order and long range order. In the beginning, we have long range order, which means that we can predict how the lattice should look like in longer distances, where in the end we have only a short range order, which means that the symmetry or we can only predict how the lattice will look like over a very short distance. So I do not have to tell you how important the superconductivity research is. Many things that we now consider essential would not exist without it, as for example MRI machines, where we have superconducting electromagnetic coils, or speeding connections between computer chips, or also the LHC, where we use superconducting coils that allow high currents to flow without electrical resistance. And it is thus very important that the phenomenon of superconductivity is thought to be understood thoroughly, as have contributed the 3 laureates of the Nobel Prize in 2003. And I say this because there are still a lot of open questions, like why and how exactly high TC superconductors work. And many groups work on this topic, and also Professor Chung's group and also Professor Schilling's group, which actually holds the department record for the highest TC measured for cuprate superconductors, which is this group right here, at ambient temperature. And the goal is to find room temperature superconductors, for obvious reasons. But how far are we from room temperature superconductors? And in 2020, actually, a group found a room temperature superconductor, but the only problem was that it operates at a pressure of 267 gigapascal, which corresponds to about 3/4 of the pressure of the Earth's center. So it's not very applicable. And there are many things that we consider theoretically possible for which the technology just hasn't been developed yet. As for example, propulsion engines for airplanes that could be made smaller and thus more efficient and quieter, or power lines around the world, which could deliver solar energy from the sunniest parts of the Earth to parts where it is nighttime, for example. And using superconducting cables, you could deliver this energy in form of electrical current without any loss. So you can see that the future of superconductivity technology is very promising, and I hope you're as eager to dive into it as I am. And at this point, I want to thank you for your attention, and I also want to thank Dr. Chi Wang for supporting me in making this presentation and finding my way through a very interesting but also very challenging topic. Thank you very much.